In the last video, we were introduced to Newton's first and second laws of motion. And we will take a look a bit more at what the second law of motion says and doesn't say about mass. So to that end, I want to start by thinking about practical measures for measuring forces. A lot of objects have a property called elasticity, which says that they exert a force that's proportional to how much it's stretched. So you can even go and engineer springs very carefully so that they'll have some relaxed length. And then if you go and stretch that spring under a load, like so, this extra distance that the spring gets stretched will be proportional to the force that's being used to stretch the spring. So we can, at least in principle, calibrate these springs. What we could do is we could take, say, a lab cart that we know has a mass of 1 kilogram. And then what we can do is we can set up motion sensors to very carefully measure the acceleration of the cart. So we can go ahead and pull on our cart until it's got an acceleration of 1 meter per second squared. Then we can go ahead and measure that stretch, and we can mark that stretch on a scale. And we can say that the force that caused that stretch was equal to 1 Newton. And then we could repeat this whole process. So we could again take our dynamics cart, and we could pull it again, but this time we pull it in a way until we achieve a carefully measured acceleration of 2 meters per second squared. So that's going to be a bigger acceleration, and our stretch is going to be longer. So let me just stretch the spring some more. And then instead of that being 1 Newton, we'd say that's 2 Newtons. Okay, and you get the idea. We can keep on a suitable schedule of accelerations. We can keep pulling our 1 kilogram cart with the spring, measuring the stretches and marking each of the stretches to calibrate the spring. So now with that, we can flip that around to use that to measure what we'll call the inertial mass of something. So now what we do is, instead of having 1 kilogram mass, we put on our dynamics cart a mass of I don't know. We still have a motion sensor, but now what we can do is apply a sequence of known forces pardon me, that looks awful. Sequence of known forces. Sure, I can spell too. F-O-R-C-E-S. There we go. And from that we read out the associated accelerations. So we'll just say we've got a list of accelerations. All right, so then what you can do is you can make a graph. You could plot your forces against your accelerations. And yes, I know the manipulating variable is the force and the responding variable is the acceleration, but just bear with me here. The reason I'm doing it this way is I'm thinking, okay, A equals F net over M, and here my only force is just the force of the spring. So if I rewrite this as F equals MA, if I put A on the x-axis and F on the y-axis, that mass will be the slope of the fit line that I draw when I plot force against acceleration. So the slope equals the mass. Now I'm willing to bet you that the last time you weighed yourself, you didn't do that. But this is what we'd have to do to measure what we call the inertial mass. So we're measuring the inertia of an object. We're measuring how hard is it to change an object's velocity. So that's what the inertial mass answers. Now, more likely than not, the last time you measured your mass, what you did was, say, if you're at let's go with you're at a doctor's office, because then that's conceptually the best. If you're at a doctor's office, you stand on that thing where they slide the little weights around. I know that you might have a newer one with digital readouts, but just work with me here. The one with the weights is effectively the same difference as if we put you on one end of a pan balance and known masses in the other end. So let's say this is the object that you're trying to measure the mass of, and then we go and just stick a collection of known masses there. What we would be measuring there is the gravitational mass. Because if you think about it carefully, what we're doing here is we're actually making a comparison of the gravitational force on the known mass against the gravitational force on the unknown mass. And once we've added enough known masses to get them equal, we say that the masses are the same. But if you think about that, that's not measuring the same thing. This is measuring how hard gravity interacts with an object. Now, if you think about it, in our operational definition of mass, we just roll with this gravitational mass right in the operational definition, right? We'd say it's that thing that a balance measures. So if you think about it, this thing where either we do the dynamics cart and we do the forces and we get the slope, this is measuring the inertial mass. Here, where we're comparing gravitational forces, we're measuring the gravitational mass. There is absolutely no reason, since these are measuring what seems to be two totally different properties of nature, there should be no reason why these are the same. There have, however, been experiments done testing how close are they to each other. The last experiment that I was aware of that was able to simultaneously measure the inertial and gravitational mass of various test objects saw that there was no difference to within the precision of the apparatus. The apparatus would have been able to detect a deviation at the part per trillion level, 1 part in 10 to the 12. Sorry, that's part per quadrillion. No. No, part per trillion, sorry. So if there was a difference at the part per trillion level, this experiment would have teased it out. It did not see any such difference. Now, that doesn't mean that there might not be a difference at, say, the part per quadrillion level, or the part per sextillion level, or the part per vinctillion level. There may be a difference between these two. But to our best ability to measure, and we've measured it very precisely, it appears that the inertial mass is equal to the gravitational mass. And so we will assume that it is. Fully understanding that maybe at some future point it isn't. But we'll deal with, we know how to deal with it if that's the case. Now, Einstein is known for his theory of special relativity. That's the thing that gives the E equals mc squared. He also had what's called the theory of general relativity, which is the current best model of gravity that we have out there. And Einstein used as his springboard this observation that the inertial and the gravitational masses seem to be the same, or at least you can state it that way. And so since his model of gravity seems to work very well, and it's built around that assumption, that gives us some additional confidence that this is the case. So when you see the m's there, when you see an m in an equation for gravitational force, in the not too distant future, we'll be writing things like F sub g equals mg. This is the gravitational mass. On the other hand, when we write things like A equals F net over m, that's the inertial mass. We assume that the two are equal, and so if we substitute one into the other, we will just go ahead and cancel the m's on the assumption that they are. All right, next time, more fun with Newton's laws. Catch you on the flip side.